Hello, I'm going to talk about climate change and its effects on the world. I'm going to start by showing you how rapidly climate is now changing, and then talk about how we might be able to do something about the impacts that climate change is having on our planet. So we can start by looking at this graph, which is only recently been developed. We now know how to be able to measure the average temperature of the Earth way back to about 1 million years ago. This is mainly because we're using the record from ice cores. That's cores taken through the Greenland and Antarctic ice sheets. So by some careful calculations with this, we're able to measure what the temperature of the Earth was like over the last 1 million years. And also, by taking very small samples out of this ice core record, we can get at the tiny bubbles which were inserted in the ice when the snow fell that produced the ice sheet. And by taking out the carbon dioxide from those little bubbles, we can work out what the carbon dioxide content was on the planet over the last 1 million years. Now, carbon dioxide is the most active greenhouse gas, the most important gas causing global warming. So it's now almost miraculous that we can say how much of this carbon dioxide there was in the atmosphere back over 1 million years. So here we see it, and what we can see is a kind of sawtooth pattern. If we look on the right-hand side here, we see that the carbon dioxide level in the atmosphere was about 280 parts per million during the warm periods. That's when the CO2 level was high, and then it dropped down slowly to a minimum of 180, and then it rose very rapidly, and that brings us up to the present day, or to 1950, because there's been a radical change in the amount of carbon dioxide in the atmosphere during the last few years, the industrial period. So if we look now at the right-hand side of the graph, we see the previous ice age, which is that low level. It rises quickly to 280. That is, the ice melted, brought us up to what's called an interglacial. That's what we're in at the moment, a warm period. And then it cooled off, and the ice came back again to the last ice age, and then it rose rapidly again to the present day. It rises quickly and drops slowly because when the cause of the ice ages, which is a wobble on the Earth's axis, that causes the ice sheets of the world to grow, but they can only grow at a certain rate, which is the rate at which snow falls on them. But when the wobble changes again and the Earth is trying to warm up, the ice and snow melt more quickly, because you can melt as much as ice as you can supply heat for, whereas when you're freezing, you can only freeze at the level at which the snow falls. So we have a kind of sawtooth pattern. We emerged from it rapidly, and that's the last few thousand years. And then the carbon dioxide level rose to this level of 280, which seems to be the level that the Earth would like to have in between glacial periods when it's warm. And so we rose to that in 1950, and then we rose much faster to an even higher level, which is the one we show here, which is over 400 parts per million. This is what is the chief cause of accelerating global warming today. Well, let's look first at what that's done to the amount of sea ice in the world. Now, we know that one of the big effects of warming is going to be ice and snow are going to melt. That will happen far faster than any change in landscapes or any change in rocks. In fact, as the current saying says, you can't argue with the melting point of ice. That's the first thing to go when the climate warms up, is ice and snow. So here we see what the situation was in the Arctic with sea ice, that's the blue substance here, what it was in the 1970s, which is when I started to do work in the Arctic. And we see that in the summer on the left-hand side, the sea ice retreats a little bit from the coastlines of Siberia and North America, but only a little bit, not usually enough for a ship to get through very easily. Then in the winter, on the right-hand side, the sea ice grows, fills the whole Arctic basin, also fills Baffin Bay, Hudson's Bay, and part of the Bering Sea, and part of the Sea of Okhotsk, all the way down to the Japanese coast. This was the standard cycle of winter versus summer in the Arctic. But on top of that was a trend which at first you couldn't really see. And this trend started, we think, in about 1900. And this graph shows how the seasonal ice cover in the Arctic changed. And we can see that the brown curve, which is the bottom one, the ice, that's the summer ice, disappeared more quickly than at other seasons of the year. So from 1900 onwards, the summer ice was retreating fast, but the ice in other seasons was retreating slowly, and people didn't really realize that the Arctic was changing. But when it changes through a large enough amount, we do realize it. And this is the difference between the way the ice was in the 1970s and the way the ice is today. On the left-hand side, the yellow line marks the summer ice limit in the 1970s, while the blue shows where the ice limit is now. So about half of the ice, or more than half, of the ice area in the Arctic that existed in the 1970s no longer exists in summer. In fact, you can very easily sail a ship through the Northern Sea Route or the Northwest Passage to get from the Atlantic to the Pacific, which you never used to be able to do. The right-hand side shows a rather smaller effect, which again is a retreat from the yellow, which was the winter ice limits in the 1970s, to the white, which is the winter ice limits today. There's still a lot of ice remaining in the winter. So that's the ice effect. But if we look at the temperature effect, we saw this big sawtooth pattern over the last million years. But when we look at the last 1,000 years, which we are again able to do from ice cores and other methods, we see, that's in the bottom graph here, that the average temperature of the Earth stayed very constant, or relatively constant, right from the period when this graph starts. That's the year 1000, when the Vikings were in Greenland. And there was a very gradual decrease, which means we're heading towards another ice age, but heading very slowly. And that lasted until about 1850, and then suddenly the temperature took off upwards. Clearly a different process is going on than was happening during the first 1,000 years of slow change. And that shooting upwards is entirely a product of the Industrial Revolution, when we started to burn coal, and burning coal produces carbon dioxide. The carbon dioxide increases the temperature of the air. This is something that people didn't initially realize was happening, but it certainly is happening. And if we expand the bottom curve and look at just the last 100 years, we see how the temperature has risen, and the there was a pause in about the 1920s, 1930s, and then it's carried on rising rapidly since then. There was no explanation for this when we first started measuring air temperatures in the 19th century. They were rising because we were burning coal and then oil, but nobody could measure that they were rising because we didn't have meteorological offices in the world. Nobody was routinely measuring air temperature. So the temperature was rising, we didn't know it. The first scientists to really show that the temperature should be rising with all this carbon dioxide going into the air was a Swedish scientist called Svante Arrhenius. And this is the famous paper that he wrote in 1896, which explained the warming of the atmosphere as being due to increased amounts of carbon dioxide being put into the atmosphere by man. And why does this happen? Well, this is a very brief explanation of why the greenhouse effect happens. The right-hand curve here shows the amount of energy being radiated back from the Earth back to the Sun. There's a balance of energy between shortwave radiation, which the Sun is emitting, that reaches the Earth, and that radiation warms the Earth, and the Earth then radiates at longer frequencies, longer periods, radiates energy back to the Sun. So the balance between the radiation from the Sun and our earthly radiation back towards the Sun is a balance which determines the temperature of the Earth. Now, when we look at that radiation balance as a function of wavelength, we see that there should be a smooth change. There's one of the laws, one of the gas laws, that's the Stefan Boltzmann law of radiation, shows that the radiation that the Earth emits as a function of its temperature should smoothly vary with frequency. But when we look at the radiation, in this case it's measured from a satellite above the Mediterranean, we see that there isn't necessarily a simple trend. Instead, we have these big dips, these holes in the radiation distribution, which is due to the fact that some of the radiation coming from the Earth is absorbed in the atmosphere and doesn't get back out towards the Sun. And the bands where this happens, the most important ones are related to the presence of gases in the atmosphere. And the biggest gap here is due to carbon dioxide. There's another one here due to ozone, and another one over here due to water vapor. But you can see that what reduces the amount of radiation going out from the Earth to the Sun, the biggest factor is that carbon dioxide in the atmosphere is absorbing some of it. So a lot less is getting out. And there are other smaller factors, ozone and water vapor and methane over here. So these gases which cause radiation from the Earth to remain within the atmosphere rather than going out back to the Sun, these are called greenhouse gases. The most important is carbon dioxide and methane, ozone, nitrous oxide, water vapor. These are less important. So we'll be talking a lot about carbon dioxide and a bit less about methane during these lectures. That's the gas content. But when we look at the effect of that carbon dioxide, we see that that's the main cause of the increased warming rate of the planet during this century. This is a blow-up which shows how much heating has occurred during the last century or so due to us burning increased amounts of coal and then oil. And we can see that the warming has accelerated and the temperature now is warmer than ever before. The temperature and the carbon dioxide content go together because the carbon dioxide, as we put it into the atmosphere, it absorbs outgoing radiation, prevents that radiation from getting out of the planet's atmosphere, so the atmosphere warms up. So carbon dioxide content and air temperature go together. But the temperature warming is not distributed equally over the whole planet, and this is important for the impacts of climate change on the frozen parts of the planet, because the Arctic warms up much more rapidly than any other part of the planet. This shows the average temperature of the Earth and the change that's happened since the 19th century, but as a function of latitude. And we can see that if we take the global average warming, we can see that in the Arctic, north of 60 degrees, it's warmed far more rapidly than anywhere else in the low latitudes or in the Antarctic. So this Arctic warming or Arctic amplification is an effect which we don't fully understand, but it is such that the Arctic is warming about 3 times as fast as lower latitudes. It really is melting very, very fast. Now we can see that not only does it warm faster, but on the rare occasions when the Earth cools down for a little while, it cools faster as well. So changes in temperature are happening faster in the Arctic than anywhere else. Here we see a period between 1890 and 2010, when for a while the air temperature over the world on average went down. There was a little bit of cooling, just happened for a short period. But when we look at the temperature in the Arctic, not only does it increase more rapidly than the rest of the world, here and here, but when the rest of the world is cooling, it cools more rapidly. So changes in the Arctic, both warming and cooling, happen more rapidly than in the rest of the world. Now, how do we know all this? Now, we know about the carbon dioxide, as I said at the beginning, by using tiny syringes, just like you use for vaccination, to extract little bubbles of gas from ice cores and work out how much carbon dioxide there is in the gas. But for temperature, the best source is measurements made on the top of a mountain in Hawaii. They also measure the present state of carbon dioxide as well. And that's a volcano called Mauna Loa. And it's extraordinary because until 1896, we didn't know that we were putting climatically active gases into the atmosphere. Then we did, because of the work of Arrhenius, but we still didn't bother to measure the temperature or the carbon dioxide content. And that didn't start until 1958 with this observatory that was put on the top of this volcano by the Scripps Institution of Oceanography in San Diego. So every day since 1958, this observatory has been measuring carbon dioxide content of the atmosphere, air temperature, and a lot of other parameters. So we depend on Mauna Loa for our present knowledge of what's happening in the world. And here's the record since 1958, and it's very important because it shows a relentless, accelerating increase in carbon dioxide content, which means, in the same way, a relentlessly accelerating level of temperature. Here we see the carbon dioxide content. The wiggles are because the carbon dioxide content varies seasonally, depending on whether it's winter or summer. But we see that the record started at a level of only 310 parts per million in 1958. Now, 280 was the level at the end of the last ice age. So everything we'd done in the 19th century, all the coal we burned, and in the early 20th century, only managed to increase carbon dioxide content by 30 parts per million, from 280 to 310. But since then, the rate of increase has accelerated. So we see now an accelerating growth, which has gone beyond 400. And these are measurements that I took yesterday, or wrote down from Mauna Loa yesterday. And on January the 24th, it was 419, which means it's up here. And exactly a year ago, it was 416. So the carbon dioxide level is increasing now at about 3 parts per million per year. So in the whole century since we started burning oil and coal, the level only went up about 30, from 280 to 310, but now it's going up at 3 per year, far more rapidly and accelerating all the time. So this is a real cause for worry. This is what we should be worrying about now, the fact that this carbon dioxide curve is accelerating upwards. And nothing we can do seems to be able to slow it down. This red line is the carbon dioxide curve, and all the little markers you have along this line indicate annual conferences about climate held by the United Nations, and these are called the COP meetings, COP, Committee of the Parties. And we see that the level of carbon dioxide continues to rise accelerated way, despite the fact that at each one of these meetings, the world has agreed that something should be done about reducing carbon dioxide emissions. And the big agreement was the Paris Climate Agreement of 2015, which is here. Here there was an earlier climate agreement and an even earlier one. So these are global climate agreements about reducing carbon dioxide levels. But we see that it doesn't matter whether you have an agreement or not. There's no change in the rate of warming. The rate of warming, the rate of increase of CO2 just continues to rise. And the Paris Climate Agreement doesn't seem to have had any impact at all. Here it is, that's 2015, this is now. And we see the rate of rise of CO2 has continued. And it will continue in the future, because if we model the fact that we're continuing to emit carbon dioxide from burning fossil fuels, then the level will increase, and that will increase warming. So here we see a set of curves showing how much the carbon dioxide will increase if we don't do anything about reducing our emissions, which is this rapid rate of increase. And if we do something about emissions, we can keep the rate of increase low. In fact, keep the carbon dioxide not increasing at all. But here we are over here now with quite a rapid increase. So we know that if we continue to fail to do something about carbon dioxide, the rate of increase will keep rising. And that translates into a temperature rise of maybe 3, 4, or 5 degrees by the end of this century. That's something which we can't tolerate. The Paris Climate Agreement of 2015, the nations of the world agreed that they would reduce their emissions of carbon dioxide to the point where the maximum amount of warming by the end of the century would only be 2 degrees. We calculated that 2 degrees is about all that the world can stand without having disastrous effects on crops, on brush fires, on the planet generally. And not only is 2 degrees serious, 1.5 degrees is something that's better. If we can keep to 1.5, it will be even better. But we can see that we're nearly at 1.5 now. And if we keep on increasing our CO2 emissions, we'll get way beyond 1.5 and into temperatures that are really serious for survivability of man on this planet. Let's look at what it's done already. We know, for instance, that the last 6 years are the hottest years ever recorded for the planet, the average annual temperature of the planet. All these previous rises are showing a rise since the beginning of the 20th century. That's when we started burning fossil fuels. The temperature's been rising, and now these last 6 years are the largest amount of rise ever. And we see that the average temperature is 1.25 degrees above the temperature at the start of the 20th century. Now that climate scientists say, well, we haven't reached the 1.5 level yet, which is dangerous. We've reached 1.25. But in reality, we should be starting to count our temperature rise from when we first started to burn coal back in the 19th century. And if we add on the rise that happened in the 19th century to this rise that happens in the 20th century, we do really reach 1.5. So climate scientists are trying to really not to pull the wool over people's eyes, but to minimize the effect. And by saying that the rise is only 1.25, it's really not true. It's really already 1.5 since the beginning of the industrial age. Now, a very clever way of looking at how the planet has warmed over the last 50 years has been to rank the temperatures in each month of the year according to which year was the hottest, which was the second hottest, which was the third hottest. So in this case, we've got a number on each month of the year from January on. We have a number which is the rank that year had. And the blue usually is cold and the red is hot. So here we see that the hottest January were very recently, 1, 2 and 3 are the very recent years were the hottest, and the older years were colder, like number 40. The 40th year is way back here. So we see generally blue on the left, which are colder, and red on the right. So this is ranking the month. And we can go through the whole year here, every month of the year. We can see which year had the hottest, say which year had the hottest October. Again, it was recent years, 1, 2 and 3 over here. And which Octobers were the coldest. It's way back in the 1970s. So you put that together and you look at the colours and you see red is on the right, blue is on the left. That is to say the hottest years are the recent years, the coldest years are the older ones. So this is just for the last 40 years, and we can see that even over that period, the Earth has grown radically warmer. Now, let's look at now, and since things are happening at an accelerating rate, if we look at this year, or last year, 2021, we had a measurement which was the hottest temperature measurement ever made on the planet. And it happened in the United Arab Emirates at a place called Sfide, and it was 51.8 degrees. That's the highest reliably measured air temperature ever. And it happened in 2021. But surprisingly, obviously in the Arabian desert, you expect it to be hot. But it was very hot last year in places that you don't expect. And the most unexpected was a town called Lytton, right up in the Rocky Mountains of British Columbia, which are usually snow-capped mountains. And I've been through Lytton many years ago. It's a small town, high up in the mountains. You don't expect it ever to get very hot, but in fact it reached a temperature of 47.9 degrees, and that was so hot that in fact the town caught fire. The trees that it was embedded in caught fire, and the entire town was burnt down by a brush fire that was due to the very high temperature. So this was extraordinary for Canada, the hottest temperature ever reached in Canada, hot enough to destroy a town. Now, the warming has been most rapid, as I showed, in the high latitudes in the Arctic. And here we see that again from a temperature record from Siberia. And we see that on the right-hand side, the red is showing that Siberia has been warming more rapidly than the rest of the world. In fact, in this region, there was a warming of 6 degrees, which is extraordinary. And what that did was to set fire to Siberia. The Siberian forest and taiga caught fire spontaneously, and some of it has been burning continuously for more than a year. And again, we don't expect that because Siberia is cold normally, it's wet, it's not a place which catches fire. But in this case, it did catch fire, and the Siberian fires have been burning continuously because it's so remote that nobody can get in there to try to put the fires out. So the biggest fire and the most widespread fire in the world is the big fire in Siberia, which is still going on. Here's another fire in a more accessible area in Pasadena, and this was one that I encountered as I was driving by, and here's this. I took this picture in August of 2019. The brush fire in a canyon caught fire and set fire to really the city. And Pasadena is a city. You don't expect a city to burn, but it did. And here it is. For several days, the freeway, which I was on, was closed, and we couldn't go anywhere until the fire had been put out. So that's showing the effect in causing fires. Another effect is that the sea ice has been, as I showed already, has been disappearing, but it doesn't just disappear in winter, in summer rather, it disappears all the way through the year. And here we have several years of record of Arctic ice extent during the spring and summer and then the autumn, so the summer months. And these values have been year-on-year values, but last year was the lowest it's ever been. That's this red line, and it's the lowest right through the year. It's not just that it's a very low value in the middle of summer, it's been a very low value all through the year. So that's what's happening now, that the sea ice is weakening throughout the year, even though the change is most obvious in summer. This is carrying on that curve into this year, and showing that again the recovery from the summer has been weaker, and the blue shows the present state of the ice, and there's a smaller area than there was at the same time last year. The world record so far loss has been in 2012, and this shows the white shows the ice limits in 2012, and the yellow is the ice limits back in the 1970s when there was more ice around. So we see the ice shrinking in summer and winter, and at some point it will disappear in the summer, first of all. Now, what are the effects of that? Well, we can see if we look at particular little bits of the Arctic, we can see changes. Now, this is an interesting part of the Arctic. It's northwest Greenland, and this is when I went with Inuit hunters who were hunting polar bears with dog sledges. So we were on a sledge with the dogs in front of us, and there's another sledge in the distance, and an iceberg in the background. But the flat white surface is sea ice, and the sea ice was thick enough for the Eskimos to hunt successfully using their heavy dog sledges. That's the way it was. That was back in about 2010. But when a colleague of mine went back last year, this is what he found. This is exactly the same location. In fact, it's exactly the same dog sledge and exactly the same dogs. So it's the same hunter going out to show how he hunts polar bears. But instead of being able to walk over thick ice, they were wading through water. And this thick layer of water lying on top of the ice is because the ice is melting, even in the winter. This is March. And very dangerous to have the ice doing this. It's not safe to run over that with a sledge because you don't know how thick the ice is. So that's a change just over a few years in winter. And northwest Greenland is the coldest part of Greenland. And this means we can't do things anymore that we used to do in the Arctic. One of the ways we study ice is to go out in the winter, set up a bunch of huts to form an ice camp, and have equipment in the huts to do observational measurements of the ice and the air and the water. So here's the place where each of these 6 people lived in each of these huts, and I was one of them. This was the mess where we ate and cooked. This was the generator hut for electricity, and this was the science hut where we did all our measurements. So this was maintained by plane and by helicopter, and you went there for 2 or 3 months in the winter, and then you came away. In fact, you generally demolished these huts, but you can't go there anymore because this solid ice called multi-year ice, which is more than a year old, which gives you a thick ice surface that's safe to work on, is no longer there. It doesn't exist anymore. And so it's unsafe to work on Arctic ice in the winter, which is makes it difficult for scientists. So what we have to do now is to freeze a ship into the ice like this, and then work from the ship so that if the ice breaks up because of warming, we don't fall through the ice. We're safely on a ship. So the measurement of how this ice thinning has happened, it's quite a difficult thing to do. You can use your satellite to tell you the area of ice, but to measure the thickness, you have to go underneath the ice and look upwards from below. So for that, you have to use a submarine, and we've been making use of Navy submarines, British Navy submarines and US Navy submarines, to go under the ice and to look upwards with an echo sounder. So this shows what it looks like to see the submarine surfacing through ice. They put us ashore so we could do that filming. Here it is emerging from the ice. and this is how we lived. It was me and a colleague doing the measurements from below, but a submarine is a military vessel. You don't have comfortable cabins, and we had to sleep here in a rack where they normally store torpedoes. Very, very uncomfortable. And the submarine also is very, very cramped. There's equipment everywhere, and this is what it's like in the control room where the submarine is controlled. Now this was the last voyage we did, and in this case we had an advanced form of echo sounder, which doesn't just give you a record of the reflections from the surface, but it gives you a proper record of the three-dimensional shape of the underside of the ice. So you mount that sonar in the top of the submarine here, and it shows you ridges in the ice, which are called pressure ridges, and here we see some of them with the ice piled up underneath. This is the older kind of measurement where you're just using a single echo sounder looking upwards, which is telling you how thick the ice is, giving you a reflection from the bottom. And we see that the ice was a mixture of thick ice, this is called multi-year ice, thinner ice, which is refrozen leads, and first-year ice, and these ridges, which are caused by the wind piling the ice up underneath to form these ridges, which can be 40 or 50 meters deep. Now, this is what the multi-year ice and ridges look like. This is what the whole Arctic looked like when I used to work there in the 1970s. But when I work there now, it's not nearly as impressive. The ice doesn't last many years, it just lasts 1 year. It's called first-year ice. It forms and then it melts. And it's very thin, as you can see. Sometimes you would fall through ice like this. So it's a completely different landscape for the Arctic than when there used to be. Big change from that to that. And that change is a change in the thickness of the ice and a change in the area. And when we combine the two, we see that the volume of the ice, that's the thickness times the area, is decreasing very, very fast. And we can see since 1970s, it's decreased to a quarter of what it was in 1979. So this is, the red line is the present volume of ice in the summer in the Arctic, and this is what it used to be. So we see a very rapid fall off of the area and thickness of ice. Well, what are we going to do about it? This is the frightening thing. The main thing is that the amount of carbon dioxide we're emitting is increasing all the time. Now, some countries are doing something about reducing their emissions. This shows the emissions from Europe, that's the blue, and the USA, which they're both showing some recent decreases. But those are more than offset by big increases in the emissions from China and India. And the reason for this, of course, is that industry in China has grown very rapidly, and we are now getting Chinese factories to make the things that we used to make ourselves in our own factories in Europe and America. So the European emissions are going down a bit, but the Chinese and Indian emissions are going up fast. You combine the two and we can see that global emissions are continuing to increase. And as I showed in that earlier graph, we have no sign that the global emissions are decreasing. And the first graph showed carbon dioxide, and now we can see that methane is also increasing rapidly, and it started to increase in the year about 1850 to 1900, with the Industrial Revolution, again because of burning coal. and it's been shooting up. And so methane and carbon dioxide are both actively contributing to the greenhouse effect. Methane seemed to come, this is some methane measurements made in the Arctic, and methane seemed to be reaching a level. It looked as if it wasn't rising anymore, and these fluctuations are just the season change. But then it started to take off again. And we see these little blobs around, and these are single blobs of methane, which we think are coming from emitters in the seabed, in the Arctic seabed. And I'll show that now. And the result of that has been that carbon dioxide has been increasing steadily and accelerating, as I showed. But methane went rapidly upwards, flattened off in the first decade of this century, but has then taken off again and is increasing even faster. So methane is growing even faster than carbon dioxide. So we start to look at what are the consequences to climate warming of this increase in CO2. The first, of course, is warming of the atmosphere. The next one is that this causes a sea level rise, which is very, very important for the planet. That is to say, global sea level is now determined by the amount of ice held in the Arctic and the Antarctic on the Greenland ice sheet and the Antarctic ice sheet. As the temperature warms up, that ice starts to melt, and the melting of that ice causes global sea levels to rise. Now we see that sea levels were rising slowly right through the 20th century, but now they've taken off, and the predictions caused by us continuing to emit greenhouse gases which are causing the ice sheets to melt are that the global sea level is going to grow in an accelerated way, and we might, from these observations and predictions, have a sea level rise of just over 1 metre by the end of this century. But as time has gone on and people have done more measurements, these measurements have got higher and higher. So the estimate of what sea level will reach by the end of this century is now gone beyond 1 metre and is gone towards 2 or 3 metres. And we can see that this loss of ice if you climb around on the Greenland ice sheet and look at it. So I was up on the Greenland ice sheet in August, the middle of summer in 2019, and this is what I saw. Firstly, there's no sign of any snow on top of the ice anymore. That's all melted away. The air temperature, which normally stays below 0 all through the year, was up to 21 degrees, enormously warm. And on that day, 12.5 billion tons of ice melted off the Greenland ice sheet. Incredible. And when you look at the ice sheet, you find that the result of the ice melting off is that a lot of dirt that was deposited on the ice sheet in previous decades or centuries is now exposed because the ice has turned into water and run away, and you're left with the dirt. And so this is called black ice. And the problem is the black ice causes even greater warming because the black ice is a bigger absorber of heat than white ice. So this black ice surface on Greenland is causing Greenland to warm even faster. And here we see black ice covering the white ice, which was the clean ice that used to be there. And we see what that's doing to sea levels. That sea level of the world is rising steadily, and it's going to be reaching levels that will cause flooding of many parts of the world, including Venice. So this global warming effect, the first impact is this increase in sea levels throughout the world. So let's look at the next effect, the sea level effect. We already see going on. When you have Acqua Alta in Venice, it's because not only is it a high tide, but it's the fact that the water in the Mediterranean stands at a higher level now. We're getting increasing amount of flooding in coastal cities, and that will get worse and worse as sea level continues to rise. The second effect is a one that I'm personally working on and very worried about, which is a methane impact. Methane, we've already shown, is one of the greenhouse gases, which is not as important as carbon dioxide, but quite important. And we've found that one of the main sources of methane now is the ocean. And this is something that worries us a lot, because if we look at the Arctic Ocean, here's a bathymetric map of the Arctic Ocean, it shows that the center of the Arctic Ocean, because it's an ocean, is very deep, 4,000 meters, that's the dark blue. But the Arctic Ocean has very wide continental shelves around the edges, that's the light blue. And these continental shelves are only about 100 meters deep, 50 to 100 meters deep. Now that's a real source of danger, because at the bottom of the Arctic Ocean, there is a very thick layer of sediment, which is made up of this stuff, which looks like ice, but actually it's methane gas dissolved in ice to produce a substance called methane hydrates. So it's sitting there as a solid material, but full of gas. If you put a match to this, it will burn. And I'll show you that later. It looks like ice which burns. But this methane gas is a really dangerous material, and it's at the moment trapped underneath the Arctic Ocean in these sediments. But as the sediments start to thaw out, and the temperature of the seabed goes up because the sea ice has disappeared, then this methane will come out of the sediments and will come up to the surface as a gas. And that's happening already. So here we see what would happen. The methane is trapped in the form of under the sediments. The sediments melt, this thaw out, and the methane escapes, comes up to the surface. And when it reaches the surface, it's turned into a gas. So it's very dangerous. You can set light to it. Here's a hole in the sea ice. You put a light to it, and it causes the methane to burn. And here's some sonar measurements, very impressive, of methane plumes. This is the seabed, about 50 meters, 60 meters down. This is the sea surface, and these are plumes of methane coming out of the seabed, rising to the surface, coming out into the atmosphere. And these plumes reflect sound waves. So this is a sonar system that measures sound waves reflected by the rising methane plumes. So this is an area 3 or 4 kilometers across, which is full of methane coming up from the seabed, rising to the surface. And if you try and set light to it, you'll get an explosion perhaps at the water surface. Here's another sonar picture of the same thing. You can see the water depth is only 70 meters. The methane comes up, it comes out of the water surface into the atmosphere. And here are methane plumes. And this is what it looks like if you actually look at it from a diver's point of view. These are the methane plumes rising in the form of individual bubbles. In this case, the bubbles are flat because they're pressing against sea ice, which is still there on the surface. And so the bubbles can't easily escape into the atmosphere. When the ice has melted, the bubbles go up into the atmosphere. And here we see a picture taken from a submarine showing the methane bubbles rising up to the surface. Well, we've now come to the end of the first half of this presentation, where we've talked about the warming of the planet, what's causing that warming, which is greenhouse gases, especially carbon dioxide and methane, and what one of the sources of methane is, which is the seabed of the Arctic, where huge amounts of methane are contained in the sediments. And as the seabed thaws out or melts because the water's getting warmer, that methane comes out into the atmosphere. There are many other sources of methane, which I'll talk about in the second half. And the main thing we're going to look at then is, can we find ways to actually get rid of these gases so that the carbon dioxide and methane content go down back to the level before the Industrial Revolution, so that the temperature of the planet should go back to the level that it was then. So instead of having really extreme heating, which is causing real danger to the survival of the human race, we might be able to go back to a climate which was more livable, the climate we had in the past, and the quite recent past, just early this century. So that's what I'm going to deal with next.